Hey everybody, it's Mr. Kramer here to present to you the number 4, the end of STARS notes. You should have your Unit 4 booklet with the notes open as you watch the video. And if at any time you need to pause the video to have some more time to take notes or to answer questions, then feel free to do so. Let's get started. Our ICANN statement for this section is to describe the evolution of low mass, medium mass, high mass, and super high mass stars, including how they form and how they die. And we'll get into how they die in this section of notes. We already learned how they form. All stars form the same way, regardless of their mass. And we did that in the number 3 notes. And so let's just look at some different stars of different masses. I've got 3 here, 3 examples: Proxima Centauri, the Sun, and Rigel. And what I want you to do is to choose one of them. And you can do this in, if you're taking the notes as a small group or individually, you can do this either way in a group or individually. But choose one of the stars, and then you're going to answer these 2 questions. How long will the star live, and what will the star become in your notes? I had planned on giving you 2 minutes. If you need more than 2 minutes, you can take however much time. But go ahead and record your answers in your notes. And then when you are ready, go ahead and continue the video. So depending on which star you chose, or if you went to compare, if you went to compare your star to another star, you would have noticed that your answer to number 1 would have been different. And stars all begin the same way, but as they age, their mass will determine how they end. Their mass will also determine how long they live. So we know stars begin the same way. They begin in a nebula. They clump together or concentrate into a protostar. When the protostar gets hot enough, fusion can begin, and it will enter the main sequence. And so we did that. Step 1, step 2, step 3. Nebula, protostar, main sequence. And that's where we left off, because step 4 through the rest of the steps is different depending on the star's mass. And so we will go through different classifications of stars based on mass, and we'll begin each classification with step 4, because steps 1, 2, and 3 are the same. So we're going to start with the lowest mass stars. These are stars with 0.075 solar masses to 0.5 solar masses. And like I said, we are doing here, right here, we are starting with step 4. So step 4 for these stars are to stay in the main sequence. They just continue to be in the same in the main sequence because, well, really, they just aren't hot enough or heavy enough to fuse anything past helium. So these stars will stay as red dwarfs for up to 1 trillion years, and they're not massive enough to fuse elements heavier than helium. Plus, they can fuse elements, hydrogen that's in the entire star, but we're going to come back to that in a moment. So Proxima Centauri, just to look at some of its characteristics, it's an M5 star, which gives you an idea of how cool it is. And I also have its temperature just over 3,000 Kelvin. And then its mass and radius as well. You can see that it's only 0.12 solar masses. So it's a very small star. But if you were comparing it to how long it's going to live, Proxima Centauri is a pretty young star. In fact, scientists have never discovered a red dwarf star more than around 10% of the way through its life. Why do you think that is? Now, you might be thinking, sir, I have no idea. Like, I really don't know. But if you think about it, if these stars can live to be 1 trillion years old, then it's impossible to be 10% of the way through its life because the universe is only 13.8 billion years old. So just the universe isn't old enough for these stars to have gotten to 10, 12, 15, 20% of the way through their lives. As I mentioned before, stars, they form these layers. We're going to learn about the layers of the sun later. And so we can actually look at this star here in the middle because it's a sun-like star. And so the sun has its core, and then it's going to have these different zones. It's got a convection zone for the sun. That's on the outside. That's where the temperature is right for convection to occur. And then it's going to have a radiative zone. Well, massive stars, the convection zone is more in the center, closer to the core. And then this yellow section would be a radiative zone where energy is getting radiated out. But for very low mass stars, they don't have a radiative zone. It never gets hot enough. And so the entire star is a convection zone. So convection is where it's kind of like if you're boiling water and you put pasta or rice in that water, and you see that as the rice and the water sink to the bottom of the pot, they get heated up because they're closer to the heating element. That actually decreases their density, so they rise. Then they get a little bit cooler, so they sink again, and they kind of go in this circular motion. Well, what that does in a very low mass star is it makes hydrogen that could be located on the outside of the star. The convection currents could bring it close to the core and be involved in fusion. And so it makes hydrogen that's in the entire star available, which is not possible in either a star like the sun or in a high mass star. So this is just one factor that causes these low mass stars to be able to live for so long. You also might be thinking like, well, how common are these low mass stars? They're really common, actually. Percentage of main sequence stars in the universe. So all of these red squares, all of the red squares, all of these are red dwarf stars. Then you have our K-class stars, which are slightly warmer, and then the G-like star, the G-class stars are here, the sun, and then you can see F, A, B, so on and so forth. The smallest percentage would be O. So about 76% of stars in the universe are these cool low mass stars like Proxima Centauri. After they've been in the main sequence for 1 trillion years, astronomers, and they've never seen this obviously, but they believe that the star will undergo some changes before it dies. So once the star fuses all of its hydrogen, the star will contract and heat up, possibly becoming a blue dwarf for a short amount of time. Then it will cool into a white dwarf, and eventually all that energy will have radiated away until the star is a black dwarf. And a black dwarf is essentially a star made of degenerate matter that's completely cooled. It's like the ashes of a star. And so this begins Mr. Kramer's thought spiral. 2 slides ago, I told you 76% of all stars in the universe are red dwarfs. So that means 76% of the universe will eventually go dark when those stars reach the black dwarf stage. No. Actually, it's worse. But all stars, I have this video from the sheet. I will post it on the Okay, at the end of your notes, there is this table, and the table is a really good summary of how stars end. And so what we're going to do is we're going to do low mass stars here. And so we had nebula, protostar, main sequence. Those are the 3 stages we did in the number 3 notes. And then we're going to add for step 4 and 5, stay in the main sequence, and then dwarf stages, death. So go ahead and fill in that left column, and we'll be filling in the medium mass column and the high mass column later. All right, let's go on to medium mass stars. These are stars that are 0.6 solar masses to 8 solar masses. And you might be thinking, wait, you just jumped from 0.5 solar masses for the low mass stars to 0.6. Well, yeah, there's some gray area. Like it's not a hard dividing line between, well, that's a low mass star and that's a medium mass star. So, yeah, how a star reacts, there's a little bit of a gray area, but we're going to go ahead and call it 0.6 solar masses. Okay, so step 4 is that the star will become a red giant. And once hydrogen fuel is gone, the core goes through these repeated cycles of shrinking, compressing, fusing, heating, and expanding. So the core is going to shrink, and when the core shrinks, the core is going to compress. Gravity is going to win for a little bit. Remember, we talked about that equilibrium balance between the outward push of fusion with the inward push of gravity. So gravity is going to win a little bit. It's going to compress the core. That's going to cause the core to get a little bit hotter and able to fuse heavier elements. And then when the core gets compressed and starts fusing heavier elements, the star gets hotter and the outside of the star will expand. And so this is going to happen over and over and over. Now, the sun is only massive enough to fuse hydrogen and helium into other low mass elements, but stars that are 6, 7, 8 solar masses would be able to fuse heavier elements as well. They would do this cycle of the core shrinking, compressing, fusing, heating, and expanding more times. So the more times that the star can do this cycle, the larger it will get as a red giant. And so the star will increase in size and decrease in temperature, changing colors. So as the star gets bigger, its surface temperature is actually going to decrease. And the star is going to go from being, like in the case of our sun, a yellow star to cooler colors like red, orange, kind of a dark orange red color. And so this is kind of the timeline of what our sun is going to be. Uh, Obviously, its birth, you can see the scale on the bottom is in billions of years, so the birth would be at 0. We're at today, right now, the sun is between 4 and 5 billion years old, about 4.5 billion years old. And then at around 9, 10 billion years, it's going to go through these cycles of the core shrinking, compressing, fusing. It'll fuse its primary element. It'll fuse, now it's using hydrogen and helium, but it will primarily fuse helium into other elements that we learned about in the number 2 notes. And it will become a red giant. So the more mass the star has, as I said before, the more times it can do this, and the heavier the elements it can fuse. So Aldebaran is a star. It's an M5 star, and I bring that up because Proxima Centauri is also an M5 star. But what's crazy is take a look at the temperature is roughly the same. Aldebaran is almost 1,000 degrees warmer than Proxima Centauri. But what's crazy is the radius, where Proxima Centauri had a solar radius of, I believe it was 0.15. Aldebaran has a radius of 45.1, so it's gotten a lot bigger over the course of its life. It also only has a solar mass of 1.16 solar masses. So we can kind of, astronomers can look at Aldebaran and say, hey, that's pretty close mass to the mass of the sun. It's likely we're looking at what the sun will become. So I went ahead and uncovered Aldebaran compared to the sun, and the sun is much, much, much smaller. So the sun will become a red giant. The question is, what will happen to the planets like Earth? Maybe you guys know. So here's today. We have the sun, Mercury, Venus, Earth, and Mars, and their distances. You can see the Earth is 1 AU from the sun. I will also post a video from Crash Course on Moodle. I'll post this video. It's really good. He kind of explains what's going to happen. It's not good. Most likely, we will be burned to a crisp. Our oceans will have boiled away as the sun is getting closer and closer to the Earth. At one point, we will be inside of the sun here in about, this says 8 billion years from now. Now, the video does mention, the video from Crash Course mentions that maybe, just maybe, if this process happens slow enough, that the Earth and Mars will be pushed out and they will no longer be in orbit of the sun. And then it's the opposite. We won't get burned up. We'll just be like these rogue planets traveling the galaxy. It would be like a freezing ice ball. I don't know which one's better. They both don't sound good, but it is the eventual fate. We've got time though. We got, like I said, about 8 billion years until this happens. So step 5, after the star becomes a red giant, some interesting things are going to happen. It depends on how massive the star is within this medium mass range. If the star is smaller, so less than 1 solar mass, the outer layers of the star will be blown off into space, leaving only a super hot, super dense core, no longer doing fusion. It's called a white dwarf star. We're going to talk more about white dwarfs in the next section of notes. If the star is larger, the energy from the white dwarf can interact with the gases that it blew out, forming what's called a planetary nebula. And so here's a good GIF of how this happens. You can see the star is pushing out gases, and then once all the gases have been expelled from the star, all that remains in the center is that red giant, and I'm sorry, that white dwarf star, the core of the star. And if those gases don't move away fast enough, the light from the white dwarf can interact with the gases, making some of the most beautiful things in the universe, planetary nebulae. So the thing is, like, why are they called planetary nebulae when they don't have anything to do with planets? And yeah, it's a great question. They don't have anything to do with planets, nothing. But like a lot of things in astronomy, here's what happened. The first people that viewed a planetary nebula were Charles Messier, the same guy that created the Messier catalog, so anything that's like M31 is Andromeda, and William Herschel. They were looking at planetary nebulae with telescopes of the late 1700s. So when they looked at them, they saw what they thought were planets. As nebulae were first being discovered, astronomers named them planetary nebulae because the shape resembled a planet. Planetary nebulae usually are round because the gases are being extinguished in all directions or being pushed out in all directions. It's stupid, but it stuck. And by the late 1800s, astronomers realized that the nebulae were clouds of dust and gas, not planets. However, the name was already there, and it didn't change. So, planetary nebulae are nebulae formed from red giant stars that have nothing to do with planets. That's just what they're called. Go figure. Like I said, we're going to talk more about white dwarfs later, but white dwarfs are interesting because they're supermassive stars. They can have a solar mass packed in the space of the Earth. So white dwarf stars are comparable to the radius of the Earth. And we'll talk more about them and how interesting they are later on. I also mentioned that planetary nebulae are some of the most beautiful things in the universe, and they really are. Um, they're really, really cool. So you can see the white dwarf stars right here in the middle. This is the Helix Nebula, 695 light years away. And that's a visible light image. The gases are moving through space from the white dwarf at 20 to 30 kilometers per second, which means that the nebula will not last forever. It's a short period of time, astronomically speaking, around 10,000 years or so. Here's another one. This is the Hourglass Nebula. How it formed is up for debate. I'm not sure. I don't think this is a visible light image. I'd have to go back and check. It says at the bottom. Oh no, it says the Hubble Legacy Archive processing by Harsh Wardham Patak. I don't know what that means. Anyways, this image was probably processed, but you can see again the gases that were expelled from the white dwarf that's highlighted in the middle with the blue color. This is the Cat's Eye Nebula, 3,000 light years away. Again, you can see the white dwarf in the middle. I guess with the round shapes, these planetary nebulae, I mean, I suppose I could see how they were believed to be planets, but still crazy. Anyways, the Ring Nebula and the Butterfly Nebula. This one's really cool too. And why the Butterfly Nebula and the Hourglass Nebula, why they're not round? Again, there are theories as to how they formed and why they formed in this way. We're not going to get into it. Just going to take a look at it and understand how beautiful they are. Okay. Uh, Eventually, the white dwarf will cool and stop glowing and become a black dwarf. And so we enter the thought spiral. This black dwarf thing is really becoming depressing. Here is the good news. There is good news. Well, kind of. mean, for the sun, this won't happen for about 1 quadrillion years. And so you understand how many years 1 quadrillion years is. I went ahead and wrote it out on the slide for you. It's a lot of years. It's a 1 with 15 zeros. So this is something that's going to happen way, way, way down the line. I think now would be a good time to go ahead and do the middle column of our uh, chart at the end of our notes. So we have nebula, protostar, main sequence, red giant, white dwarf and or planetary nebula, and then the black dwarf and death in 1 quadrillion years. Okay, guys, what we're going to do here is we're going to stop here, and we're going to pick up with this when I return. We've got a few slides left, but I think we're going to have the time to do it. And then we'll also get into some of these stellar phenomena. So, guys, stop here. We'll finish up together, and I will see you guys soon.